Okay. All right. So, as I said a minute ago, but didn't have the camera on, this unit is going to be about something called electric potential, which I'm sure maybe one or two of you know is the same as, we know another word that we use for electric potential that maybe you might have heard of before. Maybe you might have heard of it like 2 minutes ago when Timothy said it out loud. But we have another word that we use when we're describing something called electric potential, and that is voltage. Voltage is a word we've all heard. We know that when we need to put a battery in our TI, what is it now? 84. TI-84 graphing calculators, you got to put, well, actually those have batteries built in now, huh? Yeah. Okay, if you're like me and you have old school calculators like this one, then we have to put in AAA batteries, which are rated at 1.5 volts. Okay. Now, really, when you're talking about a battery or a source of energy, you're really talking about a voltage difference, right? If you have a battery that's rated at 1.5 volts, that means the positive terminal is at 1.5 volts. Does anyone know what the negative terminal is at? 0 volts. Yeah. It can be negative. Voltage can definitely be negative, but in a battery, your typical power source, it's some positive value and then some zero, and then 0 on the other end. Before we get to voltage difference, though, we want to understand from a physics perspective the concept of voltage or electric potential. And I'm going to be using the word electric potential more often now when we're talking about the theory, the theoretical side, and then when we get to the practical side with circuits and capacitors, then we'll be using the term voltage a lot more. But the reason it's called electric potential is because it's very closely related to electric potential energy, which, as we know, is very closely related to work. If I do 10 joules of work on this mass and it starts from rest and it ends at rest, change in kinetic energy is 0. So the net work I did is equal to the negative of the network or the work I did is equal to the negative of the work gravity did. Remember, we learned about all that. But I've also stored potential energy, gravitational potential energy. So if I do 10 joules of work, there's 10 joules of potential energy, right? If I let go of it, that potential energy starts turning to kinetic energy. The same thing happens with electric charges. Electric charges have mass. They are affected by electric fields. If you take a positively charged object like this guy here, and you bring another positively charged object, and let's assume that big Q here is fixed, and I want to bring in little q and push it until I get to this location, a distance r from big Q, and I've indicated the position of Q relative to big Q with a position vector r. If I want to do that, I got to do work, because I know that if I'm pushing a positive Q in towards this charge here, there's going to be a repulsive force because positive charges repel each other. So in order to move Q from infinity or from sufficiently far away that we can assume it's the same as infinity, to bring it to this location, I have to do work. Can we all understand that? And if I do work to bring that object into that location, it now has potential energy. Because what happens if I let go of it? It zips off that way, right? And because I've stored electric potential energy, whenever I let go of it, it flies away and it gains kinetic energy while it loses the electric potential energy. So it's very similar to lifting a weight and then letting it go, or pulling a bowstring back, right, and then letting it go. Potential energy after you do work, and then that potential energy goes to kinetic energy. If Q was negative, it'd be kind of the opposite, right? I would have to actually push this way as I'm bringing it in if I don't want it to just fall into big Q. So I'd have to exert a force that way instead of this way. And so I'd actually be doing negative work, right? Whereas the electric force would be doing positive work. And that situation is very, and imagine that if I started with a negative Q right here on the surface and I wanted to push it away, right? That's just like gravity. That's just like fighting against gravity. If this is the Earth, and I have a little tiny moon, or Death Star, and I want to move it away, then I actually got to push in this way, that way, because there's an attractive force there. So electricity operates, and they're both inverse square laws, so that they almost work exactly the same. The only difference is that instead of mass for gravity, we have charge for Coulomb's law. And whereas gravity is always attractive, so far as we know, electric forces can be attractive or repulsive, right? So, let's actually talk about calculating how much work I would have to do to bring Q from infinity. And remember, I say this all the time, but I just want to drive the point home. When I say infinity, I just mean sufficiently far away that the distance is essentially, that it's so far away we can approximate it as being infinitely far away. In practical sense, that could be the end of this hall, maybe. It could be on the other side of the room, right, depending on the amount of charge. If I was to charge this guy up, and I'll show you, I'll charge it up. This isn't a Van de Graaff generator, by the way. This is just a metal ball that's on an insulating stand. We will play with the Van de Graaff generator in the coming days. This isn't on the camera. So it's just a metal ball. If I charge this metal ball, it can't hold a lot of charge, as we'll learn. A spherical object really can't hold a lot of charge before it just ends up leaking it into the environment. Like this far away. If I have a little charge maybe this far away, that's essentially infinitely far away. Okay. Maybe not quite infinitely far away, but definitely on the other side of this hallway, it would be, you could, for all practical purposes, you could say it's infinitely far away.
Machines are good at holding electric charge if spheres aren't.
Sheets of charge that are placed next to each other where one's positive and one's negative. Those can hold a lot of charge. And that's what a capacitor is. You can have a spherical capacitor, but as we'll see, like to have the same charge storage capacity as a capacitor like this one, you would need spheres in the spherical capacitor that are like city size or Earth size, right, to have the same capacitance. We'll learn about that when we study capacitance, right after we learn a little bit about potential. You can't do capacitors without electric potential first. Okay. All right. And you can't do potential before you do potential energy. So what I'm going to do is ask you the question and then answer it. How much work must you do to bring a point charge from infinity to location R right here? So, what's that? A bit. A bit. If this was a Van de Graaff generator, you know the thing with the belt makes your hair stand up, and this was 1 coulomb of charge, it would be quite a bit.
Oh, yeah.
It would be quite a bit, because 1 coulomb is a lot of charge. Right. We'll talk about that in a little bit too, but just we just want to look at the theory now. We want to look at the theoretical aspect of this. Again, this isn't a practical situation that you're going to encounter on an everyday basis as an electrical engineer. However, electrical engineering, the entire process, the entire mathematics, the entire theory regarding electrodynamics in general starts from this very strange situation that you don't commonly see in real life, but from which we use to derive all the equations that we then use for actual engineering purposes. Okay. So how much work must you do to bring a charge, little q, to within R of big Q? Now we must know that in order to do this, we have to, and I'm saying Gianni, you got that charge little q in your hand and you're moving it in to a distance R from big Q. So you are applying an applied force. So let's put FA. You're going to put an applied force. When the object is at infinity, when it's infinitely far away, it essentially has zero potential energy, right? Zero potential energy. And so we want to move it in, and as we move it in, it gains potential energy. But then when Gianni gets it to this location, he stops, and the charge stops. So we're going to assume that the charge starts at 0 velocity, ends at 0 velocity, and so the network has to be 0, right? Because the object's kinetic energy didn't change. So the work that Gianni did can't be the only, or the force that Gianni exerted to bring that charge to within R of big Q can't be the only force, because if it was the only force, it would have picked up kinetic energy by the work energy theory. So what other force is acting on the charge as Gianni's pushing it in? The electric force, which is just going to point in the opposite direction, right? And by the time we get that charge to that location, the electric force, as long as we didn't push so hard that Q leaves your hand a little bit and then comes back, as long as it stops with your hand, the network has to be 0. So the electric force had to do the same amount of work as the applied force, okay? The same magnitude of work. Now, as we bring that charge in, we can calculate the work by doing the dot product of the force and the displacement. And from a calculus standpoint, we add up all of the works that are done as the force moves the charge through each infinitesimally small displacement dr from infinity to location here. And so as that happens, you have little small drs, right? And going from infinity to this location here, you just have an infinite number of infinitesimally small drs, and the forces acting on them are going to do work over each of those little tiny increments, and then you add them all up by doing the integral, and you get the total work done. Okay. So let's start our theoretical foray into electric potential energy, which then we will use to lead into electric potential, by calculating the work done by U. So that's the work done by the applied force. And we just use something that we know. We already know to calculate work, it's the integral of the force dot dr. And remember, dot products are scalars, gives us a work, which is a scalar. And we're going to be going from infinity to position R. We go from R equals infinity, way out there, to R equals R, which is just right there. And if we're talking about the work that you're doing, or Gianni's doing, then it's going to be the applied force, dotted with dr. Now, if Gianni's doing positive work, we would have to say that the electric force is doing negative work. So that the total work, the net work, is 0, which we know is the case if the charge doesn't change kinetic energy. So I can also say the work that you do to create this configuration of charges, because to put Q here doesn't take any work, right? As long as you neglect its mass. You can move any, if there's no electric field, then you flick a little charge and it's going to move forever, right? It's not going to be deflected by electric fields. So it doesn't take any work to put this first charge here, as long as its mass is negligible. But it is going to take work to get a second charge in, or third charge, or fourth charge. Okay. So to get this guy in here, you do this amount of work. Gravity, electricity, not gravity, the electric field does the negative of that. From a theoretical standpoint, what do you think we want to deal with? The applied force or the electric force when we're deriving equations for electric potential energy? Electric force. That's the more general force, right? That's the force that if I have a charge here, I can calculate the electric force at every point by determining the electric field, and then determining and then using that electric field strength, which we know how to deal with now, in combination with any charge present within that field, I can use to determine the electric force. The applied force, well, that just depends. Gianni could have been pushing hard at one point, and then pushing a little softer, and then harder, and then softer. And so it's like changing speed as it moves. And so, yeah, sometimes you're doing a little more work than the electric force. Then you're doing a little less work than the electric force. But by the time you get here, you've done the same magnitude of work as the electric force. So we can either calculate Gianni, the work he did, but Gianni's force is not really conservative, right? The electric force is a conservative force, so the rules that govern conservative forces are at play. That's something to note. I can bring the charge directly into here, or I can go in some weird zigzag motion, and I can make a couple loops around Q and then put it right here. The work that Gianni did, because it's not really conservative, it's probably not going to be the same magnitude as the electric force. But I can know for sure, because the electric force is conservative, that all we care about is not the path that it took to take Q from infinity to this location, but just the starting and ending point. Starting at infinity, ending at this location. We can just assume that it came straight in from the electric force's point of view. Okay. All right. Now you might say, you might be able to, since you guys are kind of learning integrals at this point, that, well, what if instead of bringing Q in and calculating the work that you did by taking the negative of the work that the electric force did, what if I just ran time in reverse? I just ran time in reverse. And I'll tell you right now, the second law of thermodynamics, which we don't cover in this class, to my knowledge, is the only physical law that doesn't work the same backwards in time as it does forwards in time. Okay. You guys learned about entropy, right, in chemistry? Right. Entropy is a lot of scientists say that entropy is literally what dictates the flow of time into the future. Otherwise, physical laws work the same backwards and forwards. Okay. But let's say I rewound it. So what that means is that if I push Q in, or I give it a force strong enough at infinity that it actually flies all the way in here before coming to a stop, okay, and then I just snap my fingers and reverse time, and then it goes back, right? Well, now the electric force would be doing positive work as the object goes not from infinity to r, but from r to infinity. Mathematically, if you know a little bit about integrals, you can say this will make sense. Well, if I just flip my limits of integration here, if instead of going from infinity to r, where I have dr's pointing this way and the electric force pointing that way, well, if I just reverse it, right, then I just go from r to infinity, and the electric force will be doing positive work during that whole time. So it'll be the electric force dotted with dr, only I go in the opposite direction. And then I drop the sign here. Notice that we're all saying, these are three different ways of calculating the work that Gianni did to bring Q into R from infinity. I can take his force, dot it with dr, and add up all those. I can take the electric force, dot it with dr as it's moving this way. The electric force is that way, dr is this way, the dot product is negative, right? We should know that at this point. The dot product is negative, the negative of that, negative times negative gives you a positive, which is we expect because we know Gianni did positive work. And then if I just reverse that, well, just run time backwards and say, well, now if I just start it from here and let it go to infinity, the electric force will be doing work in the same magnitude that it did bring it in, just opposite direction, opposite sign. And then I just flip the limits of integration. Mathematically, that's how I make sense of that. So instead of going from infinity to r, I just go from r to infinity, in which case this dot product is positive. Because if I'm going from r to infinity, the force is that way, so is dr. So are all the little tiny drs. Okay. So you with me? This is I can say it's super high level stuff, but this is weird. It's weird to think about. This is pretty advanced ideas. Okay. Now it turns out we have an equation for the electric force, correct? We all know what the equation is. I'm going to go ahead and use K instead of 1 over 4 pi epsilon naught, even though 1 over 4 pi epsilon naught is what's on the formula sheet. But let's go ahead and calculate the work. Done from, and now we're saying the work done by Gianni, or the work done to establish this configuration of charges. But I'm going to use this formula for it, because this is the one I have an equation for. Do we have an equation for the force Gianni exerted on the object as a function of position? No. But I do have an equation for the electric force.
If you have all the numbers, we could find it, though.
Yeah, you'd have to take a lot of data, and then you'd have to model that data with the function, and then, or you could just use Coulomb's law, in which case we wouldn't need to do any of that. So the work done would be the integral of the integral from r to infinity of the electric force. And first, before we even do that, because the electric force is conservative, I can just assume we came in a straight line. It doesn't matter if we did or not. We could have come in into some strange direction. Could have been deflected. Again, we could have orbited around Big Q a few times and just ended up here. But because the electric force is conservative, this is the beauty, and this is what makes it very convenient for dealing with conservative forces. The electric force is conservative, so I can just assume, whether it's true or not, that I brought charge little q from infinity to this location in a straight line. Okay? And it doesn't matter if you didn't do that, the network's going to be the same as if you did. So what that tells me, whenever I evaluate Fe, the electric force dotted with dr, that's just going to be F dr times the cosine of the angle between them. Well, if we're going from r to infinity, we're going this way. Electric force is this way. Dr is that way. So the angle between them is 0. So it's just going to be 1. Right? So Fe dot dr is simply F dr. president. Right? So this integral becomes just the integral from r to infinity of f dr. The electric force, dr, F E dr. All right, well, we have an expression for the electric force. It is K times big Q times little q over r squared times dr. Hey, look at that. Our force is a function of position, and we're integrating with respect to position, which is nice. And if you're like me, you rewrite integrals before you actually do them because you're very afraid of making mistakes, because I make mistakes a lot. I don't know if you guys have noticed that. Once or twice. So I'm going to rewrite this integral. First, I'm going to pull out the constants. K is a constant, Q is a constant, little q is a constant, times the integral from r to infinity. I don't like integrating 1 over r squared. I like integrating r to the negative 2. And then integrating r to the negative 2 gives me r to the negative 1. So it's going to be r to the negative 1 divided by negative 1, right? If you want to show all the steps. Evaluated from r to infinity, which is going to be k big Q little q times, and I'm even going to do this step. Well, that's going to be times negative 1 over r from r to infinity, right? Because I know I'm going to be plugging an infinity in, and even though I know r in the numerator here is technically in the denominator, visually that's going to throw me off. Because I can put infinity in the denominator, because anything divided by infinity approaches what? 0. You don't want to say equals 0, right? Because infinity is really not a number. So it's going to be k big Q little q times negative 1 over infinity minus negative 1 over r. And as we pointed out, negative 1 over infinity is pretty much 0. And minus negative 1 over r is just plus, or that is a positive 1 over r. And so the work that Gianni did to bring little q into the presence of big Q is equal to the potential energy that is now stored, that can be liberated if Gianni just lets go of big Q and little q shoots off, gaining kinetic energy at the expense of this potential energy. And that's going to be the result that we have here, which is k big Q little q over r. That's potential energy.
That's literally just the force equation times r.
Yeah.
Isn't that the equation for, or like a similar equation for the gravity version?
Yes, exactly. Yep. And I'm going to talk about that too. Only K is big G and the Q is... Now this could be written, and let me show you how it's written on the formula sheet actually. On the formula sheet it says UE. And we'll talk about this in a second. Not today actually. Maybe today. Probably not though. It's equal to... This is as it's written on the formula sheet. Q times capital V, which we'll get to next week. Which is equal to 1 over 4 pi epsilon naught, otherwise known as K, times Q1, Q2 over R. Okay, that is the potential energy. That's what's on the formula sheet. We'll talk about what QV means next week. Cool beans?
Does it get any more complicated if you add a third cube?
Yeah. I mean, it's not that complicated, but it gets tedious. And that'll be, Mr. Fullerton will talk about that in a video, and he'll show an example problem on how to do that. No, if you know this equation, then you can just use this equation. Let's say we want to bring another charge in to this. Actually, I shouldn't jump the gun. When we get to electric potential, it becomes a little easier. Whenever we can Because here we're talking about forces and potential energies of actual objects. Just like the electric field takes electric forces and then eliminates the need for having actual charges involved to do an analysis, right? We can now describe the space. Electric potential does the same thing for electric potential energy. It negates the need to have actual charges there, and it lets us describe the space around it with not a vector field, but a scalar field, right? Electric potential will be a scalar field. If I got a positive, hey, look, if you have a positive charge, actually, I'm jumping the gun. Stop it. I'm jumping the gun. Because before I want to get there, I just want to remind you, this is a great place to remind you. So let me put a little red star. Reminder. The equation that you're going to have to use on the AP exam, I'd bet a lot of money on it. I would, not going to, but I would. That's not on the formula sheet, which is that the force, an expression for force as it relates to potential energy. Do you remember? If you have a potential energy function and you want to know the force based on that potential energy function, Bradley, you should remember. You remember everything. That's why you don't take notes. What's the relationship between force and potential energy? You don't remember.
Is it a derivative?
Yes. A negative derivative.
Is the negative derivative of u with respect to time? Or
Not time.
This.
Position.
Oh.
Yeah. And this again, this isn't on the formula sheet. This is how it's usually written. Yeah. And this works here though. Because watch. What if I and notice that I have, potential energy as a function of position, right? And I started from a force standpoint, and kind of got potential energy from that. Well, you can go the other way and get force from potential energy. So if we know the potential energy function, but I'm going to go ahead and use this so I don't need to write 1 over 4 pi epsilon naught. What if I want to calculate an electric force based on the function that describes the electric potential energy of an object, little q, as a function of position from big Q? Well, I just do the negative derivative with respect to position of this. Okay, big Q, little q, over r. All right, well, that's the negative derivative with respect to position of, and actually, if I was doing this derivative, I would pull out the negative k, big Q, little q, times the derivative with respect to position of r to the negative 1. By the power rule that we learned several years ago when you guys were just small humans. Take the power, bring it out in front. The negative 1 times the negative gives you a positive. Okay, Q. And then you subtract 1 from it. R to the negative 1 minus 1 is r to the negative 2, which is 1 over r squared. So it's over r squared. Which is Coulomb's law. Right? Isn't that neat? Isn't that neat? Good times, right? All right, we do have time, so let's actually jump into potential. Any questions? So just like electric fields, I already said this, but I just want to reiterate it. Electric forces and how they operate on objects requires that objects actually come in, right? If I put this charge Q here, it generates a field. If I want to talk about electric forces associated with that field, I got to actually bring in a Q and measure the force on the Q. But when I eliminate the need to have that Q at a location within that field, I can still describe the space around big Q by invoking the concept of the field, the vector field, the electric vector field, right? I can do the same thing. If I want potential energy actually stored in this system, then I got to bring in a charge. I got to bring a charge in the presence of another charge to get potential energy. You don't have potential energy if you only have a single charge. Okay. And so I got to bring in a charge, but what we can do is, without bringing in that charge, I can actually describe the space around big Q if little q wasn't there by eliminating the need for having a Q. I think I'm circular. Okay. I just eliminate. Wait, what's going on? Okay. My computer's spazzing out. I eliminate the dependence on having a Q actually there to talk about potential energy, and then I can go and talk about potential. The electric potential or voltage is just like the electric field, only it's a scalar field because potential energy is a scalar. But I don't need to have a little q here to talk about or mathematically describe the electric potential field surrounding charge big Q. Okay. That's what I was trying to say, and I stumbled, and I apologize. Okay.
I'll never forgive you.
Oh, stop it. Note that, Johnny mentioned it, the real formula for gravitational potential energy. Before we jump into potential, let me just bring this up. Is negative G m1 m2 over r squared. Notice when we did it with a positive charge and a positive charge, our result was positive. We had positive potential energy.
Isn't it over R? No.
Yeah, there's no 2 there.
There's just an illusion.
Yeah, it's just an illusion. Yeah, sorry about that. Notice when we had 2 positive charges, we ended up with positive potential energy, right? Because we had to do positive work. What if you have a positive charge and a negative charge, and you want to bring the negative charge from infinity in to that? Well, I got to push this way, right? I got to push opposite so I can slow it down, so I can stop it when it gets there, right? And so all the signs be flipped. For one of the Q's, you put in a negative, so every result would just have a negative in front. So you'd have to do negative work. So you'd store negative potential energy. Same thing with masses because they gravitationally attract, right? If I want to bring a mass little m here into the presence of mass big M, I would have to be pushing this way, right? Pulling that way to keep it from just falling in. Does that make sense? And so I would get negative there too. Now, what does negative potential energy mean? Is kind of difficult to think about because, until you're in big kid physics, you think of potential energy as being mg delta y, right? Or mgh, right? Mass times gravity times height. Well, that requires some reference point. It requires some reference point from which you're making your measurements. This tells you the gravitational potential energy for any 2 objects in the universe, no matter where their location is. It is universal, okay? To derive this, we do a very similar, pretty much the exact derivation that we just did whenever we were talking about the 2 charges getting configured. But the difference is that because it's an attractive force, the force is going to be opposite to dr, and you're going to get a negative value. Okay, starting from a reference point that's the same. What reference point did we start from when we moved a charge in to position r? We started at infinity. So the only common reference point, that's the power of this equation here, right? If I want to know the change in potential energy here at the surface of the Earth, well, I have to measure it from the starting point. Well, if I want an equation that universally applies to the potential energy between any 2 objects anywhere in the universe, I use this equation because this equation is derived using the only reference point that is equidistant from every single object in the universe. That's infinity. We will revisit this a little bit at the end when we review a little bit for the mechanics exam. But yeah, just understand that's the big kid version for gravitational potential energy. And yes, it is negative. All right. Stop getting sidetracked, Johnny. So let's talk about electric potential. We saw that the electric potential energy is essentially the integral from r to infinity, right? We just flip, we go backwards, so we have less negatives to deal with. Just so you guys know, there's going to be a lot of negative issues, like negatives, plague, electric potential difference calculations. So just be ready for that. So we go from R to infinity of the electric force dotted with dr. It is a scalar. That's why when we get to potential, we're talking about a scalar field, not a vector field. Well, let's just consider this situation. We got plus q. Let's assume it's fixed. It's a large amount of charge. Little plus little q is going to be a little tiny charge. Sometimes they call it test charge when you're talking about the theory. You just like imagine that you're bringing a little tiny infinitesimally small amount of charge. You call it a test charge, right? And so let's say this is a really tiny infinitesimally small charge. We'll call it a test charge. If I just divide both sides of this equation by that charge, I just divide this by that charge little q, and I divide this whole side by little q, but I can just put that little q under the electric force. Well, what have I done? I have just now eliminated the need to have little q, right, at this location, if I make sense of what this equation now will tell us. Well, look at the units for this. Look at the units for this quantity here. It is the potential energy per, which means divide in math language, unit of charge. Potential energy per unit of charge. Just like I can describe a certain level above the ground as having a certain amount of potential energy per unit of mass, right? I want more potential energy at this location. I put more mass at that location, right? Because I have essentially, I have a certain amount of potential energy per unit of mass. I want more, then I just put more mass there. I now have more potential energy, right? This is potential energy per unit of charge. I want more potential energy here. Well, I got to put in more charge. That's all that means. But this is a very important, this simplifies so many things. And it is kind of abstract, which kind of sucks, but it does make so much sense whenever you actually start having to deal with circuits and stuff. You don't want to deal with electric forces all the time and the actual charges when you're talking circuits, because you have uncountable numbers of charges flowing through a circuit, and you want a more convenient way of describing that motion. And so talking about not the potential energy of a charge, a single charge or collection of charges, you want to talk about the potential energy per unit of charge. And then you just deal with that, and it's much easier. So this is what is called electric potential or voltage. And he gets the symbol capital V. What's that?
That's why it's VQ on the formula.
Yeah. Exactly.
So joules per coulomb?
Joules per coulomb is the unit, yes. So if you have a 1.5 volt battery, for every coulomb of charge, you have 1.5 volts, or 1.5 joules of potential energy. If you have a 9 volt battery, has a lot more. Has 6 times as much. Am I doing my math right?
Yeah.
9 volt battery has 6 times as much energy per unit of charge, which is why if you put the 9 volt battery on your tongue, you can actually feel it. Has anyone ever done that?
Yeah.
Because the terminals are right next to each other, you can put them on your tongue. Because your tongue is conductive, you can feel the current running through it. It's fun. I don't recommend doing that, but it's really not dangerous.
That's how I was told to test if the battery was still working.
What's that?
That's how I was told to test if the battery was still working.
Or you can use a battery tester.
Yeah.
It's hard to do that with a D or C or AA, or you can't really do that with your. I don't know if you'd feel it because there's not enough potential energy per unit of charge probably to get that charge to flow. Okay.
Or just short circuit and see if it catches fire.
Yeah. If your circuit catches fire, there's probably something wrong. All right, now we'll end about here. What's this?
That's the electric field.
That's the electric field. Now we're relating scalar fields to vector fields, and we don't care about this charge. When we're talking electric fields, we're describing the space around this guy, regardless of this guy. When we're talking potential, we're talking about the potential to have potential energy around this guy, regardless of this guy. Right? Does that make sense? That's the whole point. That's the whole point here. And so, the equation for electric potential is the integral from r to infinity of E dot dr. The electric field dotted with dr. This in and of itself isn't very useful, because electric potential isn't important. It is important, but it's not going to drive a circuit. Right? Have you ever taken two batteries and put one of them in wrong and realized that nothing's working? Because if you take two positive terminals of a battery and stick them together, and then you take a wire from the negative terminal here and the negative terminal here, no electricity flows. And that's because the electric potential doesn't matter so much. The electric potential difference matters. You need a difference in electric potential in order to drive electric current. Okay? So this just tells you the amount of electric potential at this point, but there has to be a potential difference to actually get the charge to move, which will happen. Because if I say, let's call this position RA, and then I just define another position as RB, by our new equation, so this is position A, or point A, point B, our equation for electric potential energy, do we have more or less potential energy here than we have here? We have more. So do we have higher or lower electric potential here than we do here? We have higher. So higher electric potential, lower electric potential, we have a potential difference. And then what does this charge do? Because of that potential difference, it accelerates from point A to point B. If these two were at the same electric potential, points A and B, charge Q would stay put. It wouldn't move. To accelerate charges, meaning to make electricity flow, you must have what we call a potential difference or a voltage difference. And very often when you're talking circuits, when someone says, when an electrical engineer says voltage, they're implying voltage difference. Okay? Because an electrical engineer knows that if you just have the same voltage everywhere, nothing's going to happen. You want something to happen, you need voltage difference. Okay? Just like you need a gravitational potential difference for a mass to spontaneously fall from one location to another. Electromagnetic what?
An EMP.
Oh, I don't know. Yeah, something like that. I don't know the specifics of that. That's way beyond the scope of this class.